So, good evening, everyone. I welcome you all to the eighth live session of the NPTEL online course, Basic Principles and Calculations in Chemical Engineering. The course instructed by Professor S.K. Majumder from IIT Guwahati and myself, Chaitra Borkar, a PhD scholar from IIT Delhi, who will be taking up this live session. Just a minute. Hello. Yeah. So, let's get started. So some general information about these live sessions is that these will be conducted every week on Tuesday from 7 to 9 p.m. for the duration of this course. Um, the recordings of these sessions have been made available to you. Uh, the links for these recording have been made available to you, and you can also access it through my YouTube channel. The structure of these sessions will be that firstly we'll go through the overview of the lectures for the corresponding week, which is the eighth week this time, and then solve some problems related to your assignment question so that it will enable you to solve the assignment question. So we start with lecture 24 and then go to 25, 25th lecture as well because they had the same topic, energy balance with heat of reaction. So firstly, some recap of the standard heat of formation. So this is the formula for that. This is calculated experimentally. Suppose you have some heat of formation for a compound and you compute it experimentally, and then you subtract it with the sensible heat which is being mm, uh, evolved. So that is how you get the standard heat of formation. So and the definition for the standard heat of formation is that enthalpy change associated with the formation of 1 mole of compound at 25 degrees Celsius, 1 atm from its elemental constituents. So suppose you need to compute the standard heat of formation of CO2. So it will be C plus O2 giving CO2. So this is the elemental form of O2 because in nature O2 exists, oxygen exists as O2. So and carbon exists as C. So this will be the heat of whatever the heat of reaction will be for this. This will be the heat of formation of CO2. Okay. So and it may be at some temperature, but if it is at standard temperature and pressure, so it will be delta Hf now. So then the standard heat of reaction can be computed using the heat of formation of the products and reactants. So suppose A plus B giving C plus D. So capital A, B, C and D are capital A and B are reactants, capital C and D are products, and small a, small b are the stoichiometric coefficients of the corresponding reactants, and small c, small d are the corresponding stoichiometric coefficients of the products. So how can you compute the standard heat of reaction using the standard heat of formation of the each of the constituting reactants and products? So this is the formula given for that, and these are the stoichiometric coefficient. So summation of stoichiometric coefficient into the standard heat of formation. This is the specific standard heat of formation, and this is the specific standard heat of formation. If you multiply it with the stoichiometric coefficient, you basically get the heat of reaction. This is not specific. Please mind that. So if this is in if these are moles, so this will be kilojoule per mole. Okay, these will be moles basically. So these will be kilojoule per mole. These have to be. You cannot multiply mole into kilojoule per kg. This has to be in kilojoule per mole, and this will be the unit will be kilojoule only. If this is kilojoule per mole, if this is joule per mole, so the unit will be joule here. Now it also discusses the Hess's law. So Hess's law of heat summation basically. So suppose you want to compute the enthalpy of this reaction C plus 0.5 O2 giving CO, carbon monoxide, and you don't know the enthalpy. You cannot, for some reason, you cannot compute you not find out the enthalpy for this reaction experimentally. So if you know the enthalpy for these two reactions, basically the combustion of carbon giving CO2, and then CO oxidation of CO2 giving CO2. So if you have that, you can compute the partial oxidation of carbon to CO. So this will be basically, you are basically doing the algebraic manipulation of these reactions. So C, negative of CO goes to this side. So this is CO. O2 and minus 0.5 O2 subtract to give you 0.5 O2. And CO2 gets cancelled. So basically you get C plus 0.5 O2 giving CO. And in addition to that, whatever their heat of reaction are for these reactions, they will also get subtracted. So if you are getting the subtraction of reaction 1 and reaction 2 to get the resultant reaction, the desired reaction, so the resultant heat of reaction will also be the subtraction of delta H1 and delta H2. So a difference of that. So that is what you get here. And this is the schematic showing, suppose there is a reaction A plus B plus C giving D plus E. This is the desired reaction. So what you can take is the root 1, that will be delta H1, you know that. Also you can take another root, suppose, so A plus B plus C giving X plus Y plus C, and then giving D plus E. So there will be some heat of reaction for this root and this reaction and this reaction as well. So the resultant of this will be this delta H1, because you need the final reaction here. So if this is unknown, suppose this enthalpy is unknown, so the final you get is delta H1 from this is equal to delta H question mark or unknown plus delta H2. That is what is written here. Okay. And if you want to find out this one, so that will be delta H1 minus delta H2. Okay. That is what's written here. So we continue with the energy balance with heat of reaction in lecture 25. So again here it is shown that heat of reaction, if it is at operating condition. So what we saw here is heat of reaction at standard conditions. This not represents that. So if we want at operating condition, because many chemical reactions happen at very high temperatures. So if that is the case, so what will be the heat of reaction at that condition will be, suppose you know the enthalpy at that of the products and reactants at that temperature, the difference of that for products and reactants along with the stoichiometric coefficient, and you add the standard standard heat of reaction to that. Suppose if reactions and also reactions are exothermic if the delta H of reaction is less than 0, and endothermic if delta H of reaction is greater than 0. So change in enthalpy basically. So suppose if there is a reaction occurring and you need to keep it at an you need to keep it at isothermal condition. So there is a reaction, sorry, occurring in this reactor, and around it there's some jacket basically. So there will be some outlet and inlet for the jacket as well. So suppose there is some reaction occurring in this reactor and this is the outside jacket to keep the condition at isothermal condition. So suppose if the reaction is exothermic, so it will release heat. So what you need to do to keep the isothermal condition is that you need to remove that heat. So you basically need to have a cooling medium here. And suppose if the reaction is endothermic, you need to provide heat, because and for it will require heat to break the bond. So basically, it will require the heat, to proceed basically. So you need to have some heating medium here in this jacket. Um, and the again the delta heat of reaction will be at the standard. Again, we reiterate the formula for delta heat of reaction from the delta heat of formation here. And the enthalpy change in a system with reaction will be, suppose you know the enthalpy at standard state, you add that, and suppose this is the process unit and the input will be 1, 2, some components 1 and 2, and the output will be some components 3 and 4. So suppose if there is a complete conversion basically, so what will be the extra added heat because of this reaction? So that will be N3CP3 plus N4CP4 dt from Tref to Tout, because that will be the output temperature, and the heat content due to the reactants is addition of heat due to the reactants is given by this term basically. So and also reactions in closed processes at constant volume. So in that case, we get that the delta U of reaction is can be found out from the enthalpy of the enthalpy change of the reaction using this formula. So, and this delta N is for the change in moles of gas components only. So suppose there is a reaction A which is solid, sorry, which is a solid, plus B which is a gas, giving C which is a gas, suppose. So whatever, so this is 2A plus 3B giving some C. So the change in moles of and this is a balanced reaction, suppose. So change in moles of only the gaseous components will be considered. So delta N will be product minus reactant. So C has 1 mole and reactant has the gaseous reactant has 3 mole. So 1 minus 3 will be minus 2 here. So for this case, delta U will be only for this case, delta U will be delta H minus of minus 2 RT. So this will be plus 2 RT for this case only. In the lecture 26, we discuss the enthalpy balance with heat of combustion. So standard heat of combustion, the definition for that is enthalpy change for 1 mole of substance completely burning in excess O2 under standard condition. The and it accounts for complete combustion basically. So complete combustion would involve carbon converting to carbon dioxide, hydrogen component, whatever it may be, H or H2. So suppose a fuel is only H2 basically. So H2 completely combusting to give a water vapor, or H if there is some fuel, suppose CH4. So all the H element, all whatever the H part is that in that fuel, that will be completely converted to H2O. So that will complete combustion H2 H2O. Whatever sulfur part is that completely combusting to sulfur dioxide, nitrogen to nitrogen dioxide. So next, from the standard heat of combustion, how can we compute the standard heat of reaction? So this is the formula for that. And you see this, there is a difference from the standard heat of formation. If we want to compute the standard heat of reaction from the standard heat of formation, is that here we have in the first term there is products, but here it is reactants. So keep that in mind. For combustion, the reactants are before the negative sign or the difference sign. So there is a difference between reactant minus product for combustion, and for heat of formation, to compute the heat of reaction, it is products minus reactants. Keep that in mind. And then the heat of reaction for constant volume experiment. Suppose there is a bomb calorimeter, you need to compute the heat of combustion using the bomb calorimeter or the calorific value. So this is the bomb calorimeter, and it operates at constant volume. So this is the apparatus for that. Suppose this is the inside of the bomb. This is the where the sample is kept, and you have the supply of oxygen, as well as you ignite this mixture basically. And whatever the heat is released, this is the water outside of that, and whatever heat gained by this water is then measured. So for heat at constant volume, basically you don't have any work, you don't have any delta K, delta P. So and there constant volume. So if there is, uh, if you even if you go for Y work is zero, because if you go for P delta V, so constant volume, so this term also gets zero. So from the heat balance, basically you get delta U is equal to QV. So QV is the heat transferred during this combustion reaction. And if there is heat of reaction for constant pressure experiment, suppose there is a flow calorimeter, not a bomb calorimeter, this is bomb calorimeter. Suppose there is a flow calorimeter, there are other calorimeters as well. So there is a flow calorimeter. So there the P delta V term would uh, would uh, would be there. So there we get delta U is delta H is, sorry, delta U plus P delta V. So there the P delta T V term will come into place, come into the picture basically, and that's how you get delta H is equal to QP. And this is um, heat transferred for the constant pressure experiment, and this is heat transferred for the constant volume experiment. So the difference between these two heats is delta N RT as well. So, and this is again, this is for gaseous components. So we start with the sample problem. So first question, the reaction for which summation of this product of stoichiometric coefficient into the uh, standard specific standard heat of formation for the products is greater than the products for the same term for the reactants. So that reaction will be endothermic or exothermic. What will be the correct answer here? So we will write the formula for standard heat of reaction. So that is, if we are given the standard heats of formation, so that is Ni delta HFI standard, and this is specific, minus summation of reactants. This is P for products, this is for reactants. This is Ni delta HFI standard and specific. So if this term is greater than this term, so delta H reaction standard will be greater than 0. So if it is greater than 0, we studied that this will be endothermic reaction. So the correct answer is option A. Next question, the reaction for which, so keep in mind these subscript here, F is for formation. And in next question, you see the subscript here C is for combustion. Okay, so we are given the standard heat of combustion, specific standard heat of combustion for each product and reactant. So if we need to compute the standard heat of reaction using these, the formula was, here it will be reactants first. So Ni delta H Ci standard, standard and specific minus summation of, this is P. Keep in mind, Ni delta H Ci and specific. So R minus P. So here if this term, so this term is greater than this term. So delta H standard enthalpy of reaction will be less than 0. So this will be exothermic reaction. The correct option is B part. Next question. Calculate the standard internal energy change for the following reactions at 25 degrees Celsius. Just a minute. So this reaction is given to us. We need to compute the standard internal energy change for this reaction, and we are given the standard enthalpy, specific standard enthalpy of formation for the reactant as well as the product. And mind you, the standard enthalpy of formation for this uh, standard the elements in their standard state. So this is O2 in its standard state. So the delta HF O2 standard O2 and specific, it will be 0. It is considered as 0. So if suppose there was N2 as well here, so N2 will be also 0 because it is in standard state. So we only require to compute the heat of reaction or enthalpy of reaction only for H2O and H2O2. So we need to compute the internal energy change. So we firstly need to compute the enthalpy change. So because we know delta U reaction standard will be delta H reaction standard minus delta N RT. Okay. So first we need to compute this. So how would we compute that? Using the enthalpy of formation. So delta H reaction standard will be, this is the product minus reactant and into the stoichiometric coefficient. So it will be 2 into delta HF H2O, sorry. So 2 into delta HF H2O standard and specific minus 2 into delta HF H2O2 specific standard. Yeah. So you put these values here. So 2 into minus 286 minus of 2 into minus 188. You calculate this. It comes out to be minus 196 kilojoules. This is in kilojoule per mole, and uh, you add this mole, so this will be in kilojoules only. So what will be the standard internal energy will be? minus 196 and delta n. So delta n is change in the gaseous change in the moles of gaseous components only. So here there is no gas. So delta n will be there is 1 mole here. So 1 minus 0. So delta n is 1 only. So minus 1 into R is 8.314 into temperature is 25 degrees Celsius. So 298 Kelvin. Keep that in Kelvin because this is in joule per mole per Kelvin. So this will be in Kelvin only. And this is in joule per mole per Kelvin. And this is in kilojoule. So we divide this by 1000. Keep the units consistent, please, while computing the correct answer. So 128.314 to 298 divided by 1000. So the answer comes out to be minus 198.477, which is equal to minus 198.48 kilojoules. So the correct answer is B part. Next question. The standard heat of formation of methane at 25 degrees Celsius and 180 for the given reactions will be. So standard heat of formation of methane we need to compute. So heat of formation of methane will be from its elemental component. So methane is the product here. This is the resultant reaction. Okay, I'm writing here. So methane is the product here. And from its elemental component. So C will be only C here. And H4, so twice of H2. Okay. So the delta HF comma CH4 at standard and specific, this is unknown. So this is the resultant reaction and we are given 3 reactions here. So if you look at this is basically combustion of methane. This is combustion of complete combustion of methane. This is complete combustion of carbon, and this is complete combustion of hydrogen. Okay, so we are given. Suppose there is some value here, but it is written as this term. So how to compute the standard heat of formation of methane? So that's what we are writing here. So so we need to compute the C plus 2H2 giving CH4 from these 3 reactions. So we need to do some algebraic manipulation here to get the resultant as this. So from these 3 we need to compute this final reaction. So this C and 2H2 need to be on our reactant side and CH4 needs to be on our product side. So basically if CH4 needs to be on the product side, if we look at this reaction, this needs to be subtracted and these needs to be added. So it will be C plus O2 giving CO2, H2 plus, sorry, 1,4O2 giving H2O. And and look at this, in this reactant side, CO2 has 1 mole, but H2O has 2 moles. So you multiply this by 2. So this will be 2H2. This will be O2 only. And this will be 2H2O. So you multiply this, okay, by 2. And then this is CH4 plus O. And this is the third reaction, CH4 plus oh sorry, this will have 2O2. This should be a balanced reaction. Okay, so uh, this is 4 correct. So this will be 2O2. Sorry, yeah. So CH4 plus 2. The question was incorrect. This needs to be 2O2. So CH4 plus 2O2 gives CO2 plus H2O. So this plus this minus this. So these will be in the product reactant side. Sorry, C plus 2H2 minus CH4. This will go to this side. These basically get cancelled because this will be 2O2 minus 2O2, so nothing here. And on this side, CO2, sorry, CO2 gets cancelled, and this is 2H2O, sorry again. So CO2 gets cancelled, 2H2O gets cancelled. So this again nothing here, only CH4 on the product side. So this is the uh, reaction for formation of CH4, methane. So what will be its enthalpy for this? So that will be also the using the algebraic manipulation of these reactions. So the resultant enthalpy will be, so this get added to this and twice of this. So this is given here as delta H2 not cap, delta H2 not cap plus twice of delta H3 not cap. Okay, and twice of that. Sorry, and subtract this one. So delta H1 not cap. So the correct relation is then this. If you want to compute the heat of formation of CH4, it will be this relation here if these reactions are given to us. So the correct answer here is D part. No, this will not be here. Sorry. Okay. So next question: the standard heat of formation from question 4 for the given values will be, suppose if we are given these values now, this delta H1 not cap, delta H2 not cap, and delta H3 not cap. So what will be the standard heat of formation for the methane? So from the previous question, standard heat of formation, the specific standard heat of formation. So that will be delta H2 naught plus 2 delta H3 naught cap minus delta H1 naught cap. Yeah. So we are given the values. So H2 is minus 393.5. H3 is plus 2 into minus 285.5 minus 890.3. This comes out to be minus 74.2 kilojoules. So the answer is written here, minus 74.2 kilojoules. Next question. The law applied to attain the standard heat of formation for methane in Q4 is it Newton's law, Kirchhoff's law, Hedges' law, or Dalton's law? So here in this question 4, we need to compute CH4 from C2 plus 2H2. And we knew the heat of combustion, we knew the heat of formation of O2. So from CO2 to C we knew, from basically C to CO2 we knew, C plus 2H2, sorry, C to CO2 we knew H2 plus 2H2O, and from CH4 to CO2 we basically knew. So if we write from CO2 to CH4 basically, and this also will be there. So this is basically Hess's law of heat summation. So we needed to compute this, and we knew this and this. So this is CO2 to H2, this is delta H1, this variant delta H1, and sorry, this is delta H2, and this is delta H3. So you can compute using the Hess's law. Oh, sorry, the answer is incorrect here. It is Hess's law. Next question. The standard heat of reaction for CaO plus CO2 giving CaCO3 can be computed using the enthalpies of the given reactions. So this is the resultant reaction we are given here, and you can compute this resultant reaction by the algebraic manipulation of these reactions here. So we need to do that. So the look at the product side. Product should be CaCO3, so this will be positive only. The reactants should be CaO and CO2. So if CO2 and CO are on the product side for this reaction, these should be negated. These should be subtracted so as to get CaO and CO2 on the product on the reactant side. So it will be, suppose if this is reaction 1, this is reaction 2, and this is reaction 3. And this is reaction 3. So we would require R1 minus R2 minus R3. And see, if you do that here itself, so negative and negative. So Ca minus Ca gets cancelled, C minus C gets cancelled. 1.5 O2 minus O2 is minus 0.5 O2 minus 0.5 O2, and sorry, plus 0.5 O2. Sorry. So 1.5 O2 minus O2 is 0.5 O2, 0.5 O2 minus 0.5 O2 is 0. So, and CaCO3 is in the product side because it is still plus. And here it is minus CO2. So, minus CO2 here will go this side, CO2, and CO again here because it is in minus in the product side. So, it comes here. So, CaO. And then the standard heat of reaction for this resultant reaction will be delta H dot reaction will be uh, this will also be capped. If these are specific, okay. So delta H cap reaction will be delta H1 cap minus delta H2 cap standard and delta H3 cap standard. So 1 minus 2 minus 3. 1 minus 2 minus 3. So the A part. Correct option is A part. Again, this will have H cap. And if these are for specific, okay. If suppose we need to compute only delta H reaction and we are given not cap, okay, only delta H1, delta H2 cap and delta H3, not cap, delta H3 standard. So that will be delta H1 standard minus delta H2 standard minus delta H3 standard. So this is not specific. This is the enthalpy of the reaction. So that is what you need to compute in the question 8 from the question 7. So delta H reaction standard will be delta H1 standard minus delta H2 standard minus delta H3 standard. So we are given the values, we write those values here. So delta H1 is minus 288 and minus so plus 94 and minus 152 plus 152 all in kilojoule, units consistent. So we compute the result here. Very straightforward in this case. So minus 42 kilojoule. We move on to the next question now. The heat of combustion at constant volume for the reaction C6H6. The reaction is overflowing in the next line. So I write the complete reaction here. C6H6 liquid plus 7.5 O2 gas giving 6 CO2 gas plus 3 H2O liquid. So we are given the states of these reactants and products as well. So you can assume that if the states are given, so it will be about either computing the internal energy or the if enthalpy is given, or it will be either computing the enthalpy if the internal energy is given. So heat of combustion at constant volume. So this will basically be delta U. Heat of combustion, basically heat of reaction at constant volume. So that will be because in bomb calorimeter we basically ignite it, so we combust it. The heat of combustion at constant volume will be delta U here, and we need to compute the heat of combustion at constant pressure. So that will be delta H. We have seen in the overview. So we are given delta U. We need to compute delta H. So delta U is equal to delta H minus delta N RT. So delta H will be delta, sorry, delta U plus delta N RT. So we are given this reaction, and this will be for gaseous components. So and product, sorry, product minus reactant. So product in the product side there are 6 moles, and on the reactant side it is 7.5 moles. So we get delta N as 6 minus 7.5. So we get minus 1.5. So we write delta U here as minus 3263, sorry, 0.9 minus, sorry, not minus, plus, in the bracket we write minus 1.5 into 8.314 into uh, it is 298 Kelvin. So temperature, and because this is in kilojoules per mole, so it will be 1000. So this is joule per mole per Kelvin. So, and this is Kelvin. So this is kilojoule per mole, because this is joule. If you see, this is kilojoule per mole per Kelvin, and you multiply by Kelvin, so it will be kilojoule per mole. So that is how you get it. Uh, so minus 3 to, sorry, 67.6 kilojoule per mole. Or you can say that this can be in kilojoule also, because this is for 1 mole of combustion of heat of combustion for 1 mole of benzene. So this can be in kilojoule as well. The value will remain the same for 1 mole, and this will be 3267.6 kilojoule only. So it is written here 0.6 because so the answer here will be 267 kilojoule only. So the correct answer here is A part. Then calculate the standard enthalpy of the reaction. So here we are given this reaction, and we are given other two reactions. So, and their enthalpies as well. So we need to compute the standard enthalpy of this reaction. So how to get this reaction using these two reactions? So this is R1, this is R2, let it be. So we need to find out, we need to get this reaction from the resultant of these two reactions. So we need Fe2O3 on the reactant side and Fe on the product side. So basically it will be this, this will be the in the negative form, and this will be in the positive form. So suppose we write 2Al plus 1.5 O2 giving Al2O3, and then we again write 2Al plus Fe2O3 giving 2Fe plus Al2O3. So if we subtract these, you need to see what will be the correct algebraic manipulation to get the resultant reaction. So I'm trying this. So 2Al gets cancelled. Fe2O3 will write here. No, Fe2O3 is in negative, so Fe2O3 comes here. And 1.5O2 will remain here because it is in positive. And Al2O3 again. We have Al2O3 and Al2O3, and basically it is in negative. Don't get confused by this positive. This is in negative only. Al2O3 minus Al2O3. So this is 0 again. And this is in negative again, minus 2Fe. So this comes here. So 2Fe plus 1.5O2 gives us Fe2O3. So we get this reaction here. So this is the resultant. Basically, if this is R2 and this is R1, so it is R2 minus R1. So basically, the enthalpy will be delta H. Reaction will be delta H. So suppose if this has enthalpy delta H naught reaction, so that will be delta H 2 naught minus delta H 1 naught. So we compute that here. So delta H2 naught is minus 1670 minus of minus 847.6. Again, all the units are consistent, kilojoule itself. Minus 8 kilojoules. So correct answer is B part. Suppose you are given the values in the units as kilojoule, but however the options are given in kilocalorie. So please, if you get the answer, don't think that you have gotten an incorrect answer. You convert that kilojoule to kilocalorie if the options are given in kilocalorie. Okay, keep that in mind. Next question. Calculate the standard enthalpy of reaction for this reaction equation given here. So 3CO plus 2O2 giving CO3O4. So this is CO is this is cobalt. This element is cobalt, and we are given the reaction. And from these reactions, we need the algebraic manipulation. From the algebraic manipulation of these reactions, we need to compute this as the resultant. So we are given combustion of CO to COO, cobalt oxide, cobalt monoxide basically. And we are given again the combustion of cobalt monoxide to give the CO3O4. So we are going from CO to COO to CO3O4. This is one route and this is one route. So basically this route is our resultant. This route is the desired one, okay? And this is one route given here. So what we have is delta H1 naught, delta H2 naught, okay? And this is delta H3 naught. So this will be delta H3 naught will be delta H1 naught plus delta H2 naught. You get it? So that is what we need to do. But you need to see what will be the correct algebraic manipulation, because here we see that this is 3CO, but here it is only 2CO. So to get 3CO from 2CO, we need to multiply this by 3 by 2 or 1.5. Okay. And here we see that in the resultant we have CO3O4 and this is 2CO3O4. Okay. So we need to multiply this by 0.5. Okay. So this will be, so we can write this as 3.5, sorry, not 3.5, 1.5 delta H1 naught plus 0.5 delta H2 naught. Okay, so this will be the resultant heat of reaction from this algebraic manipulation. So I can write also here. So 1.5 into 2 will be 3 CO plus 1.5 into O2 is 1.5 O2 again, and 1.5 again 3 COO, and 0.5 into 6 will be 3 COO plus 0.5 O2, giving us 0.5 into 2 again CO3 O4. So perfect values we are getting here. So 3 CO we are getting here, so we write and we add this. So 3 CO, okay, and then 3 CO and 3 CO on both the sides, so it will get cancelled. And 1.5 O2 plus 0.5 O2 will be 2 O2, giving us product on this side CO3 O4. So this is the resultant, and you get the resultant enthalpy also from this relation. So we write that 1.5 into minus 475.8 plus 0.5 into minus 355. So minus 891.2 kilojoules. So the correct answer is C part. Next question. Calculate the standard enthalpy of reaction for 2SO2 plus O2 giving twice of SO3 using the given data. So we are given these two reactions. We need to compute again. This should be the resultant of that. So we look at this. So it is going from S to SO2 and S to SO3. So S to SO2 we know, S to SO3 we know. We need to compute SO2 to SO3. Okay. So if we look at this, delta H1, delta, suppose this is delta H2 naught, this is delta, sorry, this is delta H1, uh, this should be cap, okay? So kilojoule per mole, okay, okay. And this is delta, sorry, H3 naught cap. So if we look at this, delta H2 naught cap plus delta H3 naught cap is equal to delta H1 naught cap. So if we need to compute this part, if we only look at this, we can write this as delta H1 naught cap is equal to delta H2 naught cap plus delta H3 naught cap. Okay, you look at this. From S to SO3 going to that, there is one route here. Okay, and another way to go from S to SO3 is through SO2. So this is route 1, this is route 1, and this is route 2. So whatever enthalpy we are getting in this direct reaction will be equal to the enthalpy of going through the indirect route. So the total enthalpy. Okay. So if we need to compute this delta H3 naught, so that will be delta H1 naught minus delta H2 naught. Okay. So again, there will be some algebraic manipulation coefficients. Okay, here. So we need to compute that. So here we are given 2SO2 and 2SO3. Okay. And here we are given 8SO2 and 8SO3. So to get that 2, we need to divide by 4 or multiply by 0.25. Again, multiply by 0.25. Again, you see, we need SO2 on the reactant side. So this needs to be subtracted. Okay. So if we write S8 is 0.25 S8 plus 0.25 into 12 will be 3. So 3O2, this will be 0.25 into 8 will be again 2. Sorry, this will not be plus, this is the arrow. So 2 SO3 and again 0.25 S8 plus 2O2 gives us twice of SO2. So we subtract this. So this gets cancelled. This will be O2. This is SO3. This remains here, and this is negative, so this comes this side, and this is 2 again, and this is. So this is the resulting, and which is the desired reaction for us. So the final, we can write this as delta H1 cap will be 0.25, not H1 cap, this is H3, sorry, 0.25 delta H1 cap minus 0.25 delta H2 cap. Okay, so that is what we will write here. Delta H3 cap will be, we write the values here, point into minus 3567 minus into minus 2775. This comes out to be minus 198 kilojoule per mole. So the correct answer is B part. Next question. The delta U at 298 K for the reaction methane, oxidation of methane basically, complete combustion of methane basically, uh, is minus 885 kilojoule per mole. Find the delta H naught for the same. So this is at 298 K, so this will be delta U naught only. So again, delta U naught is given to us. So we can write delta H naught is delta U naught plus delta N RT. So we can compute that. We are given minus 885. And what will be delta N here? Again for gaseous components only. So we do not consider this. We only get 2 minus this 2 and minus this 1. So all gaseous components will only be considered here. So 2 minus 3 will be minus 1 delta M. So, sorry, minus 1 into 8.314 into 298 divided by 1000 again, because this is in kilojoule. Okay. So this comes out to be minus 889.95 kilojoule per mole. Oh, sorry, this is not, sorry. This is 1 minus 2 minus 1. So 1 minus 3 will be minus 2. Sorry, yeah. Plus. So yeah, my bad. Minus 2. So this will be minus 889.95 kilojoule per mole. Okay. Next question. The reaction here is, so we are given this energy diagram here. So this is energy of the reactant is at a higher point and the energy of the product is at the higher point. So what will be the reaction? Will it be exothermic or endothermic? So basically EP minus ER, you can write delta H. Okay. So if EP, so this is at a lower point. So EP is less than ER. So delta H will be less than 0. So this is exothermic. Okay. So the correct answer here is exothermic. Next question. Find the difference between the heat of reaction at constant pressure and at constant volume for the following reaction at 25 degrees Celsius. So with the option are given in the RT form. So we know heat of reaction at constant pressure and constant volume, that will be delta N RT. So we need to only compute the delta N basically. So we are given all are in gaseous form. So delta N will be 2 minus 1 minus 2. 2 minus 2, so minus 1. So basically minus RT. So correct answer is B part. Next question. Heat of reaction at constant volume is equivalent to change in enthalpy or internal energy. What will be the correct answer here? At constant volume, okay? So QV will be delta U we have seen. So the correct answer is change in internal energy. Any questions? Anybody? If there are no further questions, I'll go ahead and close this session for today. Thank you everybody for joining.